Welcome, St. Paul American School Clark Grade 9 students, to today's explainer. Okay, let's dive into this. Today, we are locking in on G9, Geometry, U06L01, Coordinate Geometry, Distance, and Congruence Review. This is a super crucial masterclass designed to tie together everything you've been learning about mapping our world mathematically. Let's get to it.
Here's our roadmap for today, just so you know exactly what mathematical buckets we're going to cover. 1. Review objectives. 2. Coordinate geometry foundations. 3. Calculating distance. 4. Triangle congruence rules. 5. A quick formative knowledge check. And 6. A concise lesson recap.
Moving right along into Section 1, Review Objectives.
Let's set the cognitive stage for what we aim to achieve today. By the end of this explainer, you need to absolutely master coordinate geometry vocabulary, confidently calculate the exact distance between any 2 points on a grid, and apply those foundational triangle congruence rules. We are essentially connecting spatial mapping with algebraic distance. Think about it. This is literally the exact same math that powers your phone's GPS and your favorite video game engines.
All right, Section 2. Coordinate geometry foundations.
So you already know your way around x and y coordinates, right? But in geometry, we use specific formal terms. The abscissa, that's your x-coordinate. Think of it as the horizontal distance of a point from the y-axis. On the flip side, we have the ordinate. That's your y-coordinate, which measures the vertical distance of a point from the x-axis. Now, it is so incredibly easy to mix these two up, so lock these definitions into your memory right now. Abscissa is x, ordinate is y.
And of course, when you cross your x and y axes, they slice up the entire Cartesian plane into 4 distinct parts, and we call these quadrants. Every single point you plot, every single abscissa and ordinate pair is going to land in one of these 4 quadrants or directly on an axis. This right here is the basic framework for all of coordinate geometry.
Which brings us to Section 3, Calculating distance. And this brilliantly illustrates how geometry and algebra meet.
Let's look at a worked example straight from the source material. Imagine you've got a line segment starting at coordinates 1, 2, and ending way up at 21, 17. How long is that line? Well, we just treat that line as the hypotenuse of a right-angled triangle. It's like a giant puzzle. Step 1, we find the horizontal distance, the difference in our x values. 21 minus 1 gives us a base of 20. Step 2, find the vertical distance, the difference in our y values. 17 minus 2 gives us a height of 15. Step 3, we apply Pythagoras' theorem, squaring both sides. 20 squared is 400, 15 squared is 225, and adding them up gets us 625. Finally, Step 4, take the square root of 625, which gives us a total distance of 25 units. See, you are quite literally just solving for the hypotenuse of a triangle.
So here's the big takeaway. That formal distance formula, it isn't some brand new, terrifying algebraic monster. Just look closely at it. It is literally just Pythagoras' theorem wrapped up into a single equation. You take the difference in your x values, you square it. You take the difference in your y values, square it. Add them together, take the square root, bam. The whole shebang is exactly what we just did in the last slide, formalized for the coordinate plane.
But here is where things go sideways, and we need to address this misconception head-on. When rushing, a ton of students will mistakenly subtract an x value from a y value. They'll look at a coordinate pair like 1, 2, and just subtract 1 from 2. No way! That is totally incorrect. You must always find the difference between the 2 y values from your 2 distinct points and the 2 x values. Never ever mix an x and a y in your subtraction step.
To stop you from making that exact mistake, here is an absolute game changer of a pro tip straight from our curriculum resources. When you're given 2 sets of coordinates, literally grab your pen and physically draw circles around your y values and draw boxes around your x values. This visual trick instantly stops you from mixing up coordinates or fumbling when subtracting negative numbers. You only subtract a box from a box and a circle from a circle. It's a simple, tactical tool that practically guarantees accuracy.
Let's move to Section 4, Triangle congruence rules, and see how this builds into the logic of geometry.
There are 4 foundational criteria for the congruence of triangles that you absolutely must have memorized. Here we go. Side angle side, or SAS, angle side angle, or ASA, side side side, or SSS, and for right triangles specifically, the right angle hypotenuse side rule, or RHS. If you can prove just one of these specific combinations perfectly matches between 2 triangles, you've logically proven that the 2 triangles are totally congruent.
meaning they are exactly identical in shape and size.
All right, let's pause for Section 5, Formative Knowledge Check.
Let's see if you've been paying attention to our mental math. If you are calculating the distance between the points 1, 2 and 21, 17, is the difference in your y values 20 or 15? I'm going to give you a few seconds to think about it. Ready? Think back to our pro tip. Circle the y values. Your y values are 2 and 17. 17 minus 2 is 15. The difference in your y values is 15. If you said 20, well, you accidentally subtracted your x values.
And that brings us to Section 6, Concise Lesson Recap. Let's cement this knowledge. Here is your fast-paced recap of today's core required concepts. 1. The abscissa, or x, and ordinate, or y, are used to plot points across 4 quadrants. 2. The distance between any 2 points is calculated by treating the line as a hypotenuse and using Pythagoras, which is exactly what gives us our trusty distance formula. And 3. Triangles on that plane are proven strictly congruent using the SAS, ASA, SSS, or RHS rules. To wrap up, I want to leave you with this final, provocative thought. Just consider how incredibly powerful it is that these 3 distinct math tools, basic graphing, algebraic formulas, and geometric logic, all weave together to beautifully map the spatial dimensions of our world. If we can map a 2D plane with this much precision, how might these exact same foundational rules evolve to map 3D space or even the entire universe? Something to think about. Thanks for joining this explainer, and keep practicing.